All right. So please leave your mics off unless you want to ask a question. Then in that case, you turn it on, you can ask, or you can ask in chat. So Peter was able to write a comment in chat, so I think the rest of you can too. So
because Peter is a member of the group, so he could.
Oh, I see. So it depends if you're a member of the group. So maybe outsiders cannot. But shouldn't most students be inside the group?
No.
No.
Because
okay.
Because this talk is held in, I think, it's not held in students group. So.
Oh, really? Whoops. Okay. Okay, that's interesting. Okay, so in that case, just unmute your mic and then say something if you have a question. I think you can raise your hand, right? Can you raise your hand? Yeah, you can. Okay, so you can. Great. Raise your hand, ask if you have a question. Just unmute your mic, raise your hand, ask a question. But otherwise, leave your mics off. Okay. In that case, Wei Lam, will just say a few words about yourself, and you can begin your presentation.
Okay, so guys, if you want to ask any question, just ask during the Q&A sessions. Just to avoid the interruptions. And hi guys, I'm an undergraduate student now, currently year 2 semester 2 students from batch 1904, and I will be talking about the Archimedes. How do the geometry approach develop to the integral calculus? I think this is such funny before the Newtons and Leibniz comes into the play. Archimedes even have developed his own way to demonstrate the integral calculus, but avoid the infinitesimal quantities. And now, we are going to the table of content, in which this concludes all my talk. So the first one, I would like to introduce what Archimedes is. And I think all of you are familiar with this person, especially his principle and his inventions or law in physics and mechanics, or even in calculus. You all learned that the Archimedes priors, right? The R equal to data. This is his works too. And we will talk about his survival works, such as the measurement of a circle, the quadratures of the parabola, and on the equilibrium of planes, and the method of mechanical theorem. These four has a close relation to the modern calculus now we have studied before. And on the equilibrium of planes, of course, is a physics stuff, but the physics stuff derive concept of the integration. And last, we will have a Q&A session. And so this is the Archimedes. And when we talk about the biography, we would like to say that the Archimedes was the world's greatest Greek mathematician, physicist, inventor, and engineer. He contributed a lot in mechanics and physics more than in mathematics. So his contribution in mathematics, not everyone knows that his contribution in mathematics that much, rather than the physics and the mechanics. And so he was born in Syracuse, Sicily, which is now the province of Italy. And he has a connection with the king of Syracuse. So this is what the story of the Archimedes principle, where he discovered the Archimedes principle in physics. Yeah. That he has a connection with the king to find out whether the crown is made of pure gold or a mixer. And next one is the important point, that he was studied in the learning capital of Alexandria, Egypt. So the learning capital is actually founded by the father of geometry, Euclid. So you can see that his work is strongly influenced by the Euclid's elements. Even many of his work, the propositions, the theorems, and the results are all pure geometry, but the idea is simple, but the way he derived is such mind-boggling. So we will see that later on. And of course, his detailed biology is believed to be lost somewhere. So we could not know many of his life, many of his details. Okay. So the overview of his survival works is the Archimedes palimpsest. It is a manuscript that Archimedes recorded his work on it. And actually, this palimpsest is believed to be lost until in the 10th century. And there's someone who copied his treatise in the original Greek onto the parchment. But after 3 centuries, there's a monk who unappreciated Archimedes' works, erased all the context and cut the pages and write some prayers onto these pages. This is because the paper was not invented at that time. So they have to write on palimpsest. And also at the early 20th centuries, people like to draw this religious imagery on 4 pages to elevate the manuscript value. Actually, it's quite ironic because the manuscript is highly valuable due to Archimedes' work, but they did that. So it's kind of they are nearly to destroy the Archimedes' work because you have to do some, because the ink, the trace of made by Archimedes has nearly disappeared. Yeah, nearly. And this white portion is actually the Archimedes text covered by a religious imaginary image. So the historians and the researchers want to decode the text. So 80% is actually quite easy. You can use the standard method to decode, but the remaining 20% is quite hard because it's covered by this colorful image, so that one could not detect the text so easily. You have to use some new techniques that's called XFR imaging to reveal the text. So after revealing the text, you have to do the translation from Greek to the other language, to the mathematical language, to see his work. So the Archimedes palimpsest contains the following publication: Measure of Circle, which talk about the effects of circles. On the equilibrium of plane, actually is a physics stuff, talk about the law of the levers and the center of gravity. The method of mechanical theorem, we will be talking about how to obtain the area of the parabolic segment and the area of the sphere by using the method by using the proposition we have derived on the equilibrium of plane. That's why I would like to recall these applications. On the sphere and cylinder, talking about the surface area of a sphere and the cylinder. On floating bodies, this is what everyone familiar with the Archimedes principle. Yeah, the spiral lines, which you will learn in calculus 1 or 2 about how to obtain the area bounded by the spirals. Archimedes spirals are equal to A data. Yeah, and the stomachus is actually a work for combinatorics about how many ways can you complete the puzzles, the 14 piece incomplete puzzles. Actually, the answer is 536. So you can see that Archimedes is actually a co-founder to combinatorics too. And there's other works such as the speech and the other stuff. So the discovery of the Archimedes palimpsest made these two, the methods and the stomachus, been revealed in this world. These two are new to us, and the other one was appeared in the other's copy. And also the works quadratures of the parabola is not included in this palimpsest, but I will talk to it later because it is quite important for the integral calculus. Okay. So the first one will be the measurement of circle. So this is the treatise that contains 3 propositions about the fact of a circle. It is intuitive. It seems nothing to us, but it is quite important. So the first one is the area of a circle is equal to the right angle triangle. So it means that the proposition 1 say that these two shall share the same area. In the algebraic formation, the area of a circle is now known as pi r squared equal to half times r times pi r. So this is quite intuitive, and it is indeed true in our sense, but for Archimedes, no, because at that time, they do not have the concept of unknown, so they could not write these propositions in a simpler language, in a mathematical language. They have to write in words. But it is true. But how do Archimedes prove this proposition? He proved this proposition using a method which what we call it the method of exhaustion. So I think this is the first time you guys hearing this method. The method of exhaustion is actually saying that if I want to prove that these two share the same area, I would like to say that this circle has an area larger than this triangle, or this circle has an area smaller than this triangle, and lead a contradiction. So this is a double contradiction proof. And yeah, of course, it's that it must fulfill some requirement too, because the realization of irrational number. So Archimedes has to do this work. And I shall not give a proof of this. But the method of exhaustion can turn out to be the epsilon delta proof, the proof that we are familiar now for the modern calculus. And the second proposition is saying that the area of a circle to the square on its diameter as 11 to 14, which means that if you have a circle and you circumscribe by a square, then their ratio is approximate to 11 to 14, which is almost approximated by pi over 4. You could check that it is correct to 2 decimal places. But proposition 2 is actually a corollary. It's not actually a corollary. It's actually a weaker version of proposition 3. The proposition 3 suggests the approximation of pi is between 22 over 7 and 223 over 71. This is approximate ratio to the pi. And I will later giving a sketch of this proof. So the sketch of the proof is as the following. So Archimedes first used the method of exhaustion to show that the pi can be approximated between the bounds of the perimeter. So do you remember the definition of pi? It is the ratio of the circumference of a circle to its diameter. So Archimedes wants to approximate the circumference of a circle by this inscribed polygon and this circumscribed polygons, which is in red and blue respectively. So it is the case that we start with regular hexagon. So you see that there's a gap between the red and blue, and now there's a regular 12 gone and regular 24 gone. Do you see that the closeness of these red and blue lines, and 48 is like almost a circle, and finally 96. And we would like to mention that the Chinese mathematician Liu Hui, after 2 centuries, also did the same works as Archimedes. And also after 1 century later, the Chinese mathematician Liu Chongzhi, using unknown methods to derive a close ratio, even stronger than the Archimedes proposition about the neat approximation of pi, which is 355 or 113. If you have enrolled in number theory course, you will know that this number is notable approximations of pi. So this is what measurement of circle. Here, it involves the concept of limit. You see that he increased the side of the regular polygon to obtain the perimeter of the circle. So this, we see that the limit has been coming in his mind. So the second one is the quadrant of the parabola, which talk about the parabola, and of course the area of a parabolic segment. So actually this is a collection of the letter to his friend Dositheus to make the propositions involve the area of the parabola by method of exhaustion again. You see this again and again. And also, before that, Archimedes has proposed the following proposition via proof, but we can verify that easily. So in this work, we would like to find the area in green. So the first proposition would be, if we are given that the chord AB, we can always find a point P such that the tangent at P is parallel to AB. In other words, this is the Lagrange mean value theorem. Yeah, we can always find that because the parabola is a continuous function. So we see the shadow of the Lagrange mean value theorem here. And this is quite intuitive. And the next proposition says that if we draw a straight line passing through P and parallel to the axis, we will bisect the line AM at N. In other words, M is the midpoint of AB. The next one is the chord QQ prime is bisected by the line PM at N. So N is the midpoint of QQ prime. And the last one is with the notation above, we can seek for this equation, Pn over Pm equal to Nq squared over Nb squared. All these propositions can be done by coordinate geometry, which you have learned in algebra and analytic geometry or in Form 6 mathematics. So follow from this proposition, so he then showed the theorem using geometric approach. So the first one is the area of the segment of parabola is 4 over 3 times the area of the triangle with the same base and height, which stating that if you want to calculate the area of this color region, you can first calculate the blue triangle and you multiply by 4 over 3, then you will obtain the area of this color region, regardless of what color it is, the color region. So it is quite amazing because if we want to calculate the area of this parabolic segment, we have to use integration, right? But Archimedes say, no, you can do it without calculus. So the first one, Archimedes. So we recall the four propositions we have stated before. So the first one is you just fix a triangle in the parabolic segment. You fix the blue triangle, and then now you find 2 points, this point and this point. So what are the special things about these 2 points? This point has a tangent line that is parallel to this line. Okay, so see my pointer, this. And this point has a tangent line which is parallel to this line. So we fix these 2 points and form a green triangle. Archimedes say that the sum of 2 green triangle is 1/4 of this sum of this blue triangle. And now we are doing the dissection step, and we could find another 4 points in here, in these 4 yellow regions, such that the point in here has a tangent line that parallel to this line in green triangle. And so we will observe that the sum of the area of yellow triangle is 1/4 of the sum of the area of green triangle. Okay, and so on. Then if you want to calculate the area of parabolic segment, it will be very easy. You just add those triangles in blue, in green, in yellow, and so on. So do you see that this is a geometric series, right? This is a geometric series. So this is the area of blue, and this one is the sum of the area in green, and this one is the sum of the area in yellow in terms of the area of the blue triangle, which is equal to 4/3 times the sum of the area of triangle. This is exactly the area of parabolic segment, which will confirm by Archimedes with the method of exhaustion. But there's a question, because Archimedes does not know about the infinitesimal quantities, so he could not easily obtain this geometric series as we were in calculus class. So how did he do that? So the next one suggests that Archimedes did that by pictorial proof. So see that there's a square here, right? So you just cut this square into four concurrent pieces, and you just do it and so on. And Archimedes realized that this square can be seen of the upper orange, the lower orange, and the middle purple, and areas. So because these three parts are actually congruent, they are the same. So each one should consist of 1/3 of the total. So this is what Archimedes evaluate the sum. And you just plus 1 and you will obtain the results in here. So isn't that quite amazing? You see that the application of limit applies in here. Although this is not a rigorous proof if we put it in modern sense, but it is quite fantastic in that entire history, because the development of the calculus was not great until 17th century. No one invented those tools for Archimedes' work. Okay, so the next one is quite a point on the equilibrium of planes, which is the physics stuff. Why do I introduce this in this talk? Because we will use that later on, and this is quite remarkable. So there are 2 books on these publications, and the first book established the law of the lever, saying that if I have 2 objects sitting on the fulcrum pivots on the blue triangle, then we have to attain m1 d1 equal to m2 d2 for the rotational equilibrium. Okay, so this is what you learn in physics class. Actually, Archimedes proposed 10 propositions to show that, and 3 axioms to show that it must be true. And if you recognize that, m1 d1 is actually the moment in clockwise direction, and m2 d2 is a moment in counterclockwise direction, because the moment in physics just say that the tendency to rotate in the direction. Okay, so we must remember this later on. And if m1 and m2 are made of same things, we just rewrite this equation as v1 d1 is equal to v2 d2. As v1 is the volume of the object m1 and v2 is the object of m2. Is the volume of m2, sorry. So and there's the first 10 propositions on the first book, and another 5 in the first book is talking about the center of gravity of some geometric object, which is parallelogram, triangle, and trapezium. So the center of gravity is a point that we will meet in the next section. And there's a second book. And there's the second book contains 10 propositions to study parabolic segment exclusively. So just now we have talked about the quadratures of the parabola, right? So we have 10 propositions to talk about this parabolic segment. So another one, we will talk about the method. The method is the most remarkable result. Just now we have talked about the concept of limit, but now we will be talking about the concept of integrations in Archimedes' mind. And actually, the method is a letter from Archimedes to Eratosthenes, and we will use the concept of infinitesimals. Archimedes does not know about these terms. He does not know about anything about calculus, but he could derive a good work. And actually, this work is thought to be lost, but it is rediscovered in Archimedes' palimpsest. And why it is called the mechanical theorem? Because it relies heavily on the law of the lever and the central of the mass. Okay, this is quite amazing that you see that the mathematical formula is derived from the physical law. So we will talk about two. We will talk about the sphere and the parabolic segment. Just now we have derived, because just now I'm providing a sketch of proof. So now I will be providing the actual proof in this book, the method. Okay. So the first one is the construction step. So we start with a parabolic segment. So we start from this blue parabola, okay, ABC, which enclosed by the line AC. And now we let the line AC bisected by D. It means that D is the midpoint of AC. And we draw this green line, which is parallel to this axis. Sorry, I should mention that the axis is vertical. Okay, it's vertical. So it parallel to the axis of the parabola, and we join AB and AD. And now Archimedes now claims that the area of the segment of ABC, it means that the area bounded by this parabola and the line AC is equal to 4/3 times the area of triangle ABC, which is the proposition that we make just now in the quadrants of the parabola. And the second step is, now we find a point F. So what's special with the point F? It is the tangent to the parabola at point C. So Archimedes was the first one who draw the tangent line other than circles at that time. And now we extend BC to K. So we extend the BC to K. And then we also extend the point K to H, such that HK is equal to CK. We will see why later, because we would like to let K be the pivot. We would like to demonstrate the law of the lever. So we would need this, okay? At the same time, we could choose an arbitrary point O on AC, and we draw a line that parallel to the axis of the parabola, which is this green plus brown line. Okay. Okay, so things are getting complicated now, and the next step is shown in Euclid elements, which we take it as granted. Don't ask me why. You just take it as granted because it is shown in Euclid elements that BD is equal to BE. Okay, we claim that. And there's another one shown in the quadrants of parabola. Also, we have AC over AO is equal to MO over OP. Okay, so we take these two as granted. And notice that we have a lot of similar triangles. Since we draw the line CK, we have a lot of similar triangles. The big triangle CDE is similar to COM, is similar to CAF. So we can derive this. We just drag it down in here. And this is equal to these two. Just use some similar property. And also MN is equal to MO. So this line is equal to this line. This is because these three are similar triangles. So we have N as a midpoint of MO and K as a midpoint of AF. Okay. Of AF. Yeah. And also, since MN is equal to NO, MN is equal to MO. So these two, since we know that they are equal, so we now move this OP to the position TG, okay? And we make the midpoint of OP to be the center of weight. Yeah, we see this as a infinitesimal strip And we move this to TG, and H is the center of mass of TG. So just now we have derived this. Yes, we have derived this. We have derived this. AC or AO is equal to MO or OP. We would like to replace this OP by TG. Yeah, because we move OP to TG. Yeah, you see the replacement here as equal to HK or KN. HK or KN. And remember that the HK is equal to CK, right? So we have to do the replacement, okay? And we just cross multiply this MO over TG is equal to HK or KN. We will get this. Okay, so we back to the diagram. We see that TG times HK is equal to MO times NK. This is the form of the law of the lever, but TG and the MO is just an infinite strip. It is just a small thickness. It is not an area. It is not a volume. It is just a line. Okay, so TG and MO is a line. But if we just accumulate all the strips like PO, you can take this PO, you can take this PO, you can take any O you want. You can find such PO. And finally, we will see, you accumulate all the strips like this, you will see the left-hand side here will become a parabolic segment. And the right-hand side is made by MO, right? MO is a line from the triangle ACF. So if you accumulate this strip infinitely, you will see that on the right-hand side, it will form a triangle ACF. Okay, so we see that we could find the area of parabolic segment by this triangle, which satisfies the law of the lever. But on the other hand, we have the dissection step, as I introduced just now. And now we introduce the centroid of triangle ACF. Remember that in physics, we always talk about the center of gravities on the fulcrums, right? So we now denoted the centroid of triangle ACF by W. And this point W has the property that you learn in high school, that CW, the ratio of CW to WK is 2 to 1. So that's why we have CK equal to 3 times KW. Of course, CK is equal to HK. We have assumed just now, but it's equal to 3 times KW. So why do we introduce the centroid? Because we would like to demonstrate the use of law of the lever. So by the law of the lever, just now we have derived the area of segment ABC times HK is equal to area of triangle ABC times KW. And we have known that CW to KW has a ratio of 2 to 1. So the ratio of KW to HK to KW is 1 to 3. Okay, we're just moving around this equation. And furthermore, we have the triangle of ACF. ACF is this big triangle is 4 times the area of this ABC bounded by this parabola. Okay, so how do we derive this equation? We just use similar triangle. There's a lot of similar triangle, like triangle CDE is similar to triangle COM, is similar to triangle CAF, and you do all the work, you could reach this result. And we're bringing it to this equation above. This should be ACF. I written it wrongly. This is ACF. If I bring this result to these equations, we will get our desired result, okay? Which is this one. The parabolic segment is in rotational equilibrium with this triangle, this special triangle, in a ratio of 3 to 1. Do you see that 3 to 1? Okay, so this is quite amazing. So with this method, you can calculate yourself the integrations of x squared between -1 to 1 or between 0 to 1, whatever you like. Just some simple function because it is a parabola. So do you see the concept of integration here? Actually, Archimedes used the concept of what we call the Riemann sum, right? You cut off this parabolic segment into infinitesimal strip with thickness approximate to 0. And you found that the strip in parabolic segment and the strip in the triangle is in equilibrium with some specific ratio. Okay. Yeah. So this is the method, the first part. And there's a second part which Archimedes is very famous to, is to derive the volume of a sphere. So the volume of the sphere has to do with the law of delivery. This is quite strict and simple. Now we consider a sphere with radius r and a cone with base radius 2r, height 2r, distance 2r away from the pivots, is equilibrium with a cylinder with base radius 2r and the height 2r, and r away from the pivots. They are actually equilibrium. And now we assume that these three things are made of same object. It means that they have the same density. Recall that on the equilibrium of plane, I have said that V1 D1 is equal to V2 D2. So we will use that later on. So we would like to prove the claim that these three objects are rotational equilibrium. So we use the moment to show that. So we now consider the infinitesimal thickness delta x in blue. So this blue disk has a thickness delta x and x away from the top. Okay, and we treat this blue disk as a cylinder because it is small enough. We approximate it as a small cylinder. And now we consider the sphere. So for the sphere, we see that the base radius r can be calculated by the Pythagorean theorem, which is r squared from here minus r minus x squared. So this is the radius, and we would like to calculate the moment. The moment is defined by the volume times this distance. Actually, it is the mass times the distance, but I have assumed that they are made of same object. So this is the volume times the distance away from the pivot. So this is the moment in terms of delta x. The x is fixed, but the delta x is fixed, is a small quantity, and the x is not fixed. You can choose any x from 0 to 2 pi. When x is equal to 0 or 2, it is actually a circle. When x is 0, it's actually a point, and when x is equal to 2 pi, it is actually the whole sphere. So do you see the shadow of the Riemann sum? Yeah. And the next one is a cone. So this is a right cone. We don't need to calculate the base radius explicitly. If this is distance x away from the top, the base radius must be x, because its length angle is 45 degrees. So that the base radius of this infinitesimal thickness of cylinder is x, and the moment is now the volume times the distance away from the pivot, which is this. And now the cylinder, the most easier case, the moment is 4x r squared pi times delta x, which is the volume times the distance away. Oh, sorry, it should be r here, right? Oh, it should be x here, yeah. I'm writing correctly. So this is the volume of the blue disk, and this x is the distance away from this pivot. Okay, and we could check that the delta m1 is plus delta m2 is equal to delta m3 for x belongs to 0 to 2 pi. So they share the same moment, right? So they share the same moment. We can use the law of level, right? So now we would like to use the law of the level with this And recall that V1, D1 is equal to V2, D2. You can refer to this one. The volume of these two geometric figures times the distance away from the spirit is equal to the volume of this cylinder times the distance away from the spirit. So we get this equation. And Archimedes actually know how to calculate the volume of the coin of the cylinder. It is well written in Euclid elements. So this immediately shows that the volume of the sphere is 4 over 3 pi r cubed. Yeah. So the concept of the Riemann sum, the infinitesimal thickness of strip, is embedded in Archimedes' mind. Of course, the methods has concluded the other work, such as the surface area of the sphere, which I do not enclose in this talk. And there are some other interesting stuff, but we see that the law of the levers relies heavily on the method. Okay, so now it is the Q&A sessions. Do you have any question to ask?
All right, so thank you, Wei Lam. For questions, I think only some people can write in chat. So I think only people who are...
Can they turn on the microphone?
Yeah, so if you have a question, you can raise your hand, I think. I think you can see you raise your hand, and you can unmute your mic. I think that's fine. Or you could maybe write a chat to either me or Wei Lam, right? You can chat me or Wei Lam directly. I think that's possible too. Okay, someone has a question? I think you can either send a chat to me or Wei Lam too. All right.
Because I'm looking from the phone. So well.
Okay, I don't see anything. So are there any questions? Any questions? Let me see. I see my phone too. Yes, either write a chat. If you can write a chat on Teams, or you can write a chat message to me or to Wei Lam. Do I see somebody trying to raise a hand? Yeah, I see a hand. SZX Max. SZX Max, who are you?
Wait.
Are you trying to say something? SZX Max? You're muted. You're muted. Can you unmute yourself?
Oh, sorry, I accidentally pressed it.
Oh, okay. All right.
So do you have a question? Oh.
All right. I have a question myself. So
yeah.
So I have to think about this. It's kind of crazy, right? That you do all these calculations and you don't even have the idea of, like, let's call this variable to be x. Like, no algebra.
Yeah.
No algebra at all.
Because the concept of the unknowns is developing during the 7th century. Actually, this is quite an interesting mathematical history. Yeah. And Archimedes does not know how to deal with that. They don't have any concept of algebraic formulation. So he have to meet his mind with the physical intuitive. Actually, he is also an amazing physicist, right?
Mm-hmm.
So everything in math can be checked by physics. I think it's quite counterintuitive for us, at least for now. Yeah.
I see. So nothing in any of the writings of Archimedes did he like mention, oh, let x be let x be this line or anything. So everything was just geometry. There's not even a single hint of like using algebra at all in any of his writings.
Yeah. If you look into his propositions, actually his propositions never contains any unknowns that we have known that about the x, the y, the d's. That the propositions are written in words, and you have to decrypt it on your own. You have to understand what Archimedes was doing at the time and why do he state this statement. Yeah.
No, that's really cool. It's very funny because in school, we learn algebra in middle school. We learn calculus in university or maybe late high school. But actually, calculus is invented much older than algebra. So Qinghao, I saw a hand. Do you have a question?
Yes. I think I can also comment on that. So the other thing they don't have in that time is the Cartesian coordinate system, like the XYZ system. So without XYZ system, it will be almost impossible to compare the length in different direction, or like compare the area of two different triangle and shapes. So for each different question, you need to find out different reasons to convince people that this and that are like have the same area or things like that. So it will be like really, really difficult for them. And as you can see that these mathematicians are almost on the edge of the calculus, because they're begin to touch the concept of infinitesimal quantities, but like they just don't have the tools to go one step more. And so that's the first thing I want to say. And the second thing is there he is in Alexandria, and that is a very special time in the history and very special location, because there's a great library there at that time, and that library basically contains all the knowledge in the known world. Like they not only people donate to the great library, they also send people far away to buy books from different part of the world. And also, if you are like a ship to visit the Alexandria, to visit the city, then all the book on your boat will be detained and then copied before they let you go. So that's how they get like literally all the knowledge in the entire world. So it's really a privilege for a mathematician like him to be like live in a city at that time. It's really a privilege. It's something really special. That's the second thing I want to say.
Okay, thank you, Ching Hao. All right, any more questions? You can raise your hand and unmute your mic. So I do have one more question for Hui Lam, if none of you have any.
Yeah.
So you mentioned some of the Chinese mathematicians who try to do similar things, right? So are their methods also like this? Like, do they just use geometry without any algebra, or did they do anything a bit differently from what Archimedes did? Like, you mentioned mathematicians who tried to approximate pi. Was there anything different from what Archimedes did?
Liu Hui did similar to what Archimedes did, but he approximates the perimeter of polygons up to, I think, about 3,000 something. Yeah, but at that time there's no calculator, right? You have to evaluate those square roots, things like that. Even Archimedes already proposed himself many inequalities that we have no idea where is that come from. But Liu Hui also did the same things, I think around 3,192. But after a century, there's a mathematician called the Zhu Chongzhi who did the same thing to calculate. And yeah, he's not doing the same thing. He's also calculating the neat approximation of pi, but using another method which we do not know because the documentation is lost. But in that time, they have no unknowns. They have another way to record the numbers. I think it is in like they use bar and the verticals to do the work, to do the calculation. They use a lot of. Do you know how many polygons that Zhu Chongzhi reached to calculate the close ratio of the approximation of pi, the close ratio of pi, which is 355 or 113. He derived about like 24,592, I think, yeah.
Just for 3 digits, to 355, you need that many polygons. That's crazy. Wow.
Yeah. And you have to use the proposition in this book. This book is in Chinese, which is the Euclid's Elements. I suggest to read this book if you are free. This book has and every propositions in the slides that has not been derived is in this book. You can see that there's a lot of work. You can borrow it from me, or if you want the English version, you can search it on net. I think there's some math lover who construct a lot of diagram for the Euclid elements. It makes the Euclid elements very fun, very interesting, and very funny, and just want you to dig in and read the book. And you know that the things in Euclidean space, the line, the point, the circle, the parallel line, all these things are not as trivial as we know in that time. Okay, actually I have more books. Yeah.
Right. Yeah, thank you, Wei Lam. Yeah, it's very interesting that you can do so much just using geometry. Like, that's really cool. Okay, if there are no more questions, it doesn't seem there are any. Then I'll say thank you. That was a really good talk. They're really well prepared. Your slides are really good. Wow. Yeah, so this is using the LaTeX Beamer. Those of you who are in my MAT 102 class will have to learn how to make slides like this. So they don't have to be as polished as Wei Lam did, but we'll learn how to make PDF slides that look like this later. I think I'll give a class on LaTeX a bit later. Anyway, all right. So let's thank Wei Lam. I guess I'm the only one you can see.
Thank you, Professor Darren, giving me the opportunity to have this talk. And if you want to learn how to draw the diagram in Beamer, just what I actually did. I actually did draw them with LaTeX. Okay, with just pure LaTeX, no MATLAB, and there's no Sage. Without any software, I will consider to teach. But yeah, I'm currently learning to draw the surface and the volume too. Actually, this is a very hard work to do. Yeah, because if I let you to see the coding, you will be like stunned because you don't know how do I start with. Yeah, and if you could learn how to use ticks to do the work, then you will not need to insert the pictures into the Beamer anymore. You just insert the ticks pictures, which is the entire coding.
Oh, that's really cool. I didn't realize that your diagrams were all in ticks. That's really impressive. Oh my goodness. So I'm not sure you see the chat, but all the professors are really impressed. Dr. Gloria says, are you using ticks? And says, cool. And Dr. Lim says, sketching a 3D object in ticks is really hard. Yeah, that's really impressive. I did not realize that. Wow. Yeah, you see all the professors are really impressed.
Ticks in 3D object is easier than animated version. Actually, I would like to do the animations, but as you have seen that the regular polygons inscribed and circumscribed is circle in black, right? Just like you see that. Actually, I try to animate it, but I think that that's not quite good to me to do that work because it will add the burdens to me for this slide. Because this is not a report. This is just a slide. So I would not want to do that.
Yeah. Well, anyway, this is really impressive. Oh, Dr. Gloria asked a question. Can you see the chat, Wei Lam?
No.
Dr. Gloria says, have you considered 3 blue, 1 browns, a Python library for animations? So I guess it's a Python library for animation that you could consider using.
I knew that, but that requires a lot of preparations before you coding those things. And actually, if I want to use the Pythons, then yeah, I don't know how to embed it into Beamer actually.
Yeah, so not sure. So Gloria, can you embed it to Beamer? Is it possible?
It is possible to embed the video clip into the Beamer, and you can choose when to play. But that's requires a lot of work because I don't know where there's many technical issues onto that, and I have to learn that Python simulations again and again. Actually, I'm not good at framing, I think.
Yeah. So anyway, that's a really amazing presentation. The slides are really good. I thought even the topics was like very well paced. You ended on time. Everything was really good. That was really super impressive. My goodness. All right. Thank you so much. So for the rest of you who are watching, if you want to give a talk, let me know. So I'm the person coordinating this undergraduate seminar, right? Or if you one of the faculty wants to give a talk to the undergraduates, that's fine too. Let me know as well. So this seminar is for like talks either by or to undergraduates, so they'll be like, I guess, easier to understand. So I believe next week Peter said that there's going to be a research talk, right? So Munir is speaking, right? If I'm not mistaken. Munir, are you here? Yeah, so next week there'll be a research talk. So that one is not very, you're welcome. The undergraduates are welcome to attend, but that is about Dr. Munir's research. Peter say something? So Peter, want to say something, I guess? Okay.
Yes, next week Munir is giving a talk on, I have to look it up, on phase tropical Lagrangian manifolds. So you know tropical geometry, that is Munir's special research topic, and he will give some related talk on that subject.
All right, thank you, Peter. Yeah, so that's a bit different. So that's a bit of a different talk than this one. So this one is more of an undergraduate talk. Next week's
Yes, this
talk
will
is
be
more of a
definitely a
research
research talk, and it will be quite difficult, I think.
Yeah. But anyway, if any of you undergraduates want to try to watch it, I think that's fine too. We've had undergraduates who attend our research talk before. Yeah, but anyway, yeah. So thank you for attending. I appreciate such a good attendance, and I guess yeah, if there's a talk next time, I'll let you know. And again, if you want to volunteer, let me know. Okay. Goodbye, everyone.
Goodbye.
Goodbye.